Do black holes grow or shrink? The answer is yes. The late physicist Stephen Hawking proposed that while black holes get bigger by eating material, they also slowly shrink because they are losing tiny amount of energy called Hawking radiation. Hawking radiation occurs because empty space or the vacuum is not really empty. It is actually a sea of particles continually popping into and out of existence. Hawking showed that if a pair of such particles is created near a black hole, there is a chance that one of them will be pulled into the black hole before it is destroyed. In this event, its partner will escape into space. The energy for this comes from black hole. So the black hole slowly lose energy and mass by the process. Eventually, in theory, black holes will evaporate through Hawking radiation, but it would take much longer than the entire age of the universe for most black holes we know about to significantly evaporate. Black holes, even the ones around a few times the mass of the sun, will be around for a really long time. Black holes are somehow able to grow constantly without changing their size. Physics might finally be able to explain why. Leonard Susskind, a pioneer of string theory, the holographic principle, and other big physics ideas spanning the past half century, has proposed a solution to an important puzzle about black holes. The problem is that even though these mysterious invisible spheres appear to stay a constant size as viewed from the outside, their interiors keep growing in volume essentially forever. How is this possible? In a series of recent papers and talks, the 78 years old Stanford University professor and his collaborators conjecture that black holes grow in volume because they are steadily increasing in complexity, and an idea that, while unproven, is fueling new thinking about the quantum nature of gravity inside black holes. Black holes are spherical regions of such extreme gravity that not even light can escape. First discovered a century ago as shocking solution to the equation of Albert Einstein's general relativity, they have since been detected throughout the universe. They typically form from the inward gravitational collapse and deaths of stars. Einstein's theory equates the force of gravity, which curves in space-time the four-dimensional fabric of the universe. But gravity becomes so strong in black holes that the space-time fabric bends towards its breaking point, the infinitely dense singularity at the black hole center. According to general relativity, the inward gravitational collapse never stops, even though from the outside the black hole appears to stay a constant size, expanding slightly only when new things fall into it. Its interior volume grows bigger and bigger all the time as space stretches towards the center point. For a simplified picture of this central growth, imagine a black hole as a funnel extending downward from a two-dimensional sheet representing the black holes are the most massive single objects in the known universe, more massive than even the sun, sometimes millions or even billions of times as massive. They are formed from the collapse of ultramassive stars and their remnants. Anything that crosses the event horizons is destined. Anything that crosses the event horizon is destined to arrive at the central singularity, increasing the black hole mass. But thanks to the combination of general relativity, which tells us how space is curved by mass, and quantum field theory, which tells us how empty space spontaneously behaves, we learn that black holes don't remain stable forever, but decay. Which one will win, the growth or decay? That's the what Steve Fitch wants to know. For a simplified picture of this central growth, imagine a black hole as a funnel extending downward from a two-dimensional sheet representing a fabric of space-time. The funnel gets deeper and deeper, so that infalling things never quite reach the mysterious singularity at the bottom. In reality, a black hole is a funnel that stretches inward from all three spatial directions, a spherical boundary surrounding it called the event horizon, marking the point of no return. Since at least 1970, physicists have recognized that black holes must really the quantum systems of some kind, just like everything else in the universe. What Einstein's theory describes as warped space-time in the interior is presumably really a collective stars of vast number of gravity particles called gravitons, described by the quantum theory of gravity. In that case, all the known properties of black hole should trace to property of his quantum systems. Indeed, in 1972, the Israeli physicist Jacob Bekenstein figured out that the area of the spherical event horizon of a black hole corresponds to its entropy. This is the number of different possible microscopic arrangements of all the particles inside the black hole, or as modern theorists would describe it, the black hole storage capacity for information. Bekenstein's insights led Stephen Hawking to realize 2 years later that black holes have temperature and that they therefore radiate heat. This radiation causes black holes to slowly evaporate away, giving rise to the much discussed black hole information paradox, which asks what happened to information that falls into the black holes. Quantum mechanics says the universe preserves all information about the past, but how does information about infalling stuff which seems to slide forever reward the central singularity also evaporate out? The relationship between a black hole surface and its information's content has kept quantum gravity researchers busy by decades. But one might also ask, what does the growing volume of its interior corresponding to in quantum terms? For whatever reason, nobody, including myself, for a number of years, really thought very much about what they. According to this scientific discussion, black holes grows and shrink by the Hawking radiations. If you have liked this video, please subscribe this channel.